So a couple more examples of a little bit more rigor of being able to take a conservative vector field and find the potential function. This first one, we have 2x cos y minus y cos xi plus a negative x squared sine y minus sine x. Let's define the coefficients of I and j respectively as p and q. And remember, p is the partial of the potential function with respect to x. Q, remember, is the partial of the potential function with respect to y. If they are indeed, or if f is indeed conservative. So let's find the partial of p with respect to y. So remember, this is our test for part A to verify conservation. Derivative of cos is going to be negative sine, so minus 2x sine y. Derivative of y is 1, so minus cos x. And then partial of q with respect to x. Partial of negative x squared, negative 2x. Sine is going to be a constant of y. Derivative of negative sine, negative cos x. Right? And those are the same, so that means that we indeed have a conservative vector field. That means we can find the potential function. Recall, to find the potential function, we are going to integrate p with respect to x, because remember, p is phi sub x. Okay, so we're just going to take this, we're going to take the antiderivative with respect to x, and that's going to give us phi. So indeed, phi is going to be the integral of 2x cos y minus y cos x dx. And don't forget that we're going to get three terms out of this. Okay, so the antiderivative of 2x is going to be x squared. So this is phi. So let's just call that phi. So phi is equal to x squared cos y. Antiderivative of cos is going to be sine. So we have negative y sine x. And we have this g of y. Right? So g of y, remember, is some function in terms of y. It's like a function of integration, not a constant of integration. We're going to find the partial of phi now with respect to y. Derivative of cosine, negative sine, so negative x squared sine y. Derivative of y is 1, so that's minus sine x. Derivative of g of y, we're just going to call that g prime of y. We're going to set that equal to the original phi of y, which is q in this case. So that's negative x squared sine y minus sine of x. And the good news is, on both sides, a lot of stuff's going to cancel. So notice that x sine y cancels, negative sine x cancels. And so in this case, g prime of y is going to be equal to 0. We're going to integrate both sides with respect to y. And that means that g of y is equal to 0 as well. Technically, it's equal to a constant, but then so is phi xy. So let me show you what happens with that, just to make sure everybody understands that there is a constant there. So here's our potential function. Phi of xy is going to be equal to, now remember, this is phi all the way back up here. Okay, so phi is going to be equal to x squared cos y minus y sine x. Now technically it's a constant, but let's just call it plus 0 or plus a constant c. Remember, phi of xy is a constant itself. It's unknown, contingent upon the values of x and y. So if we were to meld that constant, let's just call it plus c, we can actually meld c back into that phi of xy, and that would just kind of go away. All right, so phi of xy is going to be equal to x squared cos y minus y sine x. And of course, just like we did in the previous example, if you don't trust your solution, maybe find the partials, and then see if those partials equal to the coefficients of I and j respectively. One thing we haven't looked at yet. What happens if we have a three-dimensional force field or vector function that is conservative? All right, so let's see what happens with this. All right, now what we're going to do is we're going to assume that this thing is conservative. All right, so we're going to assume conservation. All right, if we wanted to test for it, we certainly could. Okay, we would just have to find the partials with respect to each of the different variables. All right, but in these cases, I'll always just tell you that they are indeed conservative. All right, so now let's just define, or let's do this. Let's just take this one, and we know that that's going to be phi sub x. We know that this is going to be phi sub y, and this is going to be phi sub z. So let's just keep our course of action, and we're going to integrate 4x e to the z with respect to x. Now if we do that, that's going to turn into 2x squared e to the z plus an unknown function. Let's call it g, y, z. All right. Now this is where and this is phi, by the way. All right, so now phi is a little bit sneaky. Okay, so this is where we have to kind of be careful with this. All right, so now what we're going to do is we're going to find phi of y. Okay, now phi of y, well, we're just going to take the derivative of what we just got with respect to y. And if we do that, well, derivative of 2x squared e to the z is 0, plus we have this unknown function g prime of y, z. Now we know that's going to be equal to cos of y. So now what we're going to do, and remember this derivative is with respect to y. Okay, so technically we could just say that this is a partial if we really wanted to. All right, so let me erase this. So we could really say that this is the partial with respect to y of some unknown function g of yz is going to be equal to cos y. Well, that means that if we integrate both sides with respect to y, so the partial of g, y, z, partial respect to y, dy, is going to be equal to the partial of cos y, dy. And that means that g of yz is going to be equal to sine of y. So we're going to hold on to sine of y because we need that as part of our solution, okay? But there's another function, right? And the other function that we know is going to be some sort of function with respect to z, right? So I'm going to call that h of z now. Right? Now it's not x comma z, it's just z because we've already taken care of the x. All right? So if we go all the way back here, remember we found all the functions with respect to x. All right, so let's just go back, and now we have that phi is going to be equal to 2x squared e to the z plus, remember we just got sine y, plus h of z. Now we're going to find the derivative with respect to z. So phi sub z is going to be 2x squared e to the z plus sine y plus nothing, because that's just going to go away, because it's our partial of y is nothing. And then h prime of z. That's going to be equal to whatever phi of z was initially, which is 2x squared e to the z. And we start to see that this is really nice. Those two cancel out. H prime of z is equal to 0, which implies that h of z is equal to 0. So finally, we get our potential function, and our potential function, xyz, is going to be equal to that 2x squared e to the z plus sine y. Remember the test, okay? The ultimate litmus test of this is to take each of the partials and see if each of the partials is equal to the coefficients of I, j, and k respectively. And we'll see that they indeed are. Okay, so let's just test this one last time. So phi sub x is going to be 4x e to the z. And if you remember all the way back up here, 4x e to the z. Phi sub y is going to be equal to cos y. And if you go all the way back up, that one's good. And then finally, the partial with respect to z, derivative of e to the z is e to the z. So we get 2x squared e to the z. And I think that was our coefficient of k. If we go back up here, 2x squared e to the z. All right, so again, every time you find these, you should take the partials just to make sure that you get the correct answer. It couldn't hurt. It's easy to take our partials. All right, so in the last two examples that we're going to work, that's going to be basically tying everything that we know so far to be able to do some of these problems with respect to the fundamental theorem of line integrals.